Hello, welcome everybody. Welcome to the Ask Abhijit show, the science edition. I hope you're all doing great. So today I'm going to take questions from the comments that you have asked in the comments, and I'm also going to take some questions from the live chat later on, or maybe in the beginning also I can take some questions from the live chat. But before we do that, let's see who all is there in the live chat with us, who all is in attendance. I can see Aman George, Arijit Banerjee, Rakshasi Raj Hai Aaj. Akash Vijay, Thakur, Pawan Kumar Singh Bais, Random Skull, Geopolitical Dube, hello. Three-way S2, Strawberry 7, Gautami, Anantpal, Vivekananda Panda, Vladimir Chavda, Steve Harvey, Bai, Hardik Thaduk, Pritam Roy, Neo Socialist, Threat Ripper, Divesh C, Anna Malai, Avinash, Vivekanand Panda, Three Ways, Tanmoy Chakravarti, Rahul Dunake, Chetan Chaudhary, Shri Vatsa, and lots of other people. With Shetty, Rakesh Bhattacharya, The World Teacher, Imran Naimi, Pinky, Inderjeet, Avinash, Crazy Brain, Rishu Raj Soni, Muthu, Shravan R, Divesh, History X Mythology, Karan, Priyanka Javalia, hello. Nitesh Singh, hello. Rudraksh Kaul, hello. Space KGB agent. Cheku Dorje from Bhutan, hello. Nice to see you. Babla Plays, Aviral Dwivedi, Vishaka Kabila, Sonia Sinha, Prakash Bhatia, Anvit Shetty, Meet Joshi, Abhigyan Nayan, Rishikesh Das Gupta, Adarsh Kumar, Malik Sayed, Jay Maharashtra, Guru Prasad, Rohit Dalmia, Joydeep Bori, and lots of other people. So I'm going to stop greeting you all here. Aparna Sathe, Ark, Aryan, everybody else. Okay. So let's take questions from the live chat first. Okay. Strawberry 7 says how to time travel through wormholes. Well, we don't know yet. Wormholes are theoretical objects. They arise from certain solutions of the Einstein field equations of general relativity. So theoretically, they should exist. We have never observed a wormhole definitively. Some of the black holes at the centers of supermassive galaxies could possibly, perhaps, be wormholes or white holes. We don't know for sure. So we haven't observed them yet. Uh, and time travel theoretically could be possible, but it would need technology way beyond anything we can imagine today. It would also require us to have access to exotic matter, like matter with a negative mass, or for example, uh, such things. What else is it? Cosmic strings, which are once again hypothetical objects that we don't know actually exist. So we would need all that to be accessible to us, and then we would need tremendous amounts of energy to perhaps reach a wormhole and so on. So it's all theoretical, but theoretically, if you have all of this and you have the incredible amounts of energy needed for this, and you have all the super advanced, hyper advanced technology needed for that, then it may be possible theoretically, right? um let's see, let's take one or two more live chat questions. After that, I'll go into the questions from the comments. Pradyumna says, what are we supposed to do if we encounter an intelligent extraterrestrial life? Well, if we observe it from far away, like if we observe signs of a clear signs of an intelligent extraterrestrial civilization several light years away, maybe 50 light years away, then we should do our best to stay as quiet and as hidden as possible. Okay, because who knows how intelligent it may be. If it detects us, then maybe it can come and conquer us. And see, super intelligent extraterrestrial life, the difference between them and us would be like the difference between us and a dog or us and a cat. We have technology and we have all these powers that for a dog or a cat would be like superpowers, would be like magic. So we essentially hold the power of life or death over these, or for all the other creatures on the planet, because we are super intelligent compared to them. Now imagine if we detect something, a civilization, an extraterrestrial civilization that could possibly be perhaps way more intelligent than us, then we should do our best to stay hidden. So that's what we should do. But what if it arrives on Earth? then there's essentially nothing we can do about it. Then see, if they are able to travel across interstellar space, thousands of, maybe dozens of light years, hundreds of light years, then they have technology clearly that is way, way, way beyond anything we can imagine. Which means that the difference between us and them on a on an intellectual or intelligence level is incredible. It's like the difference between a human and a dog or a cat or a sparrow. So in that case, there's nothing we can do, nothing much we can do. So yeah, but if we detect it far away, we should stay hidden. Stay hidden, keep our heads down. That's what we should do. Let's take one more question from the live chat, and then I will go into the um, questions from the comments. And lots of questions about things that are not related to science, as always. But I'll take questions about science today. Um, let's see, what else? What else? What else? Shreyan says, can atoms be prepared artificially? Um, well, if you had access to individual quarks, then you could take those quarks. See, quarks are subatomic particles that are the building blocks of all matter we understand. Quarks and electrons are what make up the entire universe that we observe, the observable universe. Okay, so protons, neutrons, they are made up of quarks, and electrons don't have quarks in them. So you could theoretically take a proton and take a number of take a number of protons, number of neutrons, number of electrons, put them together, and then you could create atoms artificially. Or if you have access to, if you are able to manipulate individual quarks, which is incredibly well, next to impossible, but if you could do that, if you had the technology, then you could create create neutrons and protons out of those, or even something stranger. But let's say you can create neutrons, protons from that, and you have electrons that fly around. So you could theoretically create artificial atoms, but those atoms would be one of the atoms that we know of, one of the elements that we know of uh, in the periodic table. Okay, now let's go into the questions that you have asked in the live chat, in the comments. Let's take question number one. Okay, this is by Feminist Slayer. If polar bears were introduced to Antarctica, could they survive? And what could be the consequences? So, this is a thought experiment. Okay, we don't want to introduce polar bears into Antarctica. Polar bears live in the northern hemisphere, in the Arctic region, in various parts of the northern hemisphere. So they are not native to Antarctica. They don't belong in Antarctica, and we don't ever want to introduce them into Antarctica. And let me explain why. So what could happen if we were to hypothetically introduce polar bears into Antarctica? Antarctica is the southern hemisphere, the southern polar cap, that region. And there's a continent there. It's called Antarctica. And what lives there? You have lots of penguins, lots of birds of various kinds. You have seals, lots of seals, and that's about it. And so it's and you have various predatory animals like leopard seals, for example, orcas, killer whales that live in the oceans. The leopard seals are large, scary seals that are predators in the region. So that's the kind of wildlife that you have in Antarctica. Now, let's say we introduce polar bears to Antarctica. What could happen? So, first of all, Antarctica is way colder than the regions where bears live. It's way colder. So, will polar bears be able to adapt to that climate? Will they be able to survive there? That's questionable. There's a question mark hanging over that itself. Now, let's say hypothetically they are able to survive. Then what happens? Then obviously they would need food to survive. So what will they do? They will start preying on the local wildlife, which is essentially penguins and seals and various other birds. And these animals, penguins, seals, etc., seals come in various species. Leopard seals are the biggest, but there are other nice, fluffier, smaller seals. So seals and penguins, they don't have any natural predators in Antarctica. And if you introduce a foreign predator in the region, it could devastate the populations of the penguins and seals, etc. So that could create a stark and rapid ecological imbalance and eventually an ecological disaster if polar bears can survive there and they start eating all these animals. So that will totally imbalance the ecological balance. It will upset the ecological balance in the region, and it could lead to a catastrophe where you have extinction of species eventually. That could happen depending on how many polar bears you introduce there. So you don't want to do that, because that's wrong. You're doing something that's unnatural, right? It could cause the extinction of species that have survived for millions of years just by human beings deciding to introduce polar bears just to see what happens. No, we don't do that. So that's what could happen. And the polar bears could come into conflict with the local predators, the oceanic predators like killer whales, orcas, as well as leopard seals. But the straightforward impact would be it could cause the extinction of various species of birds, penguins, seals, etc. And that's not something desirable. As it is, the environment, the planet is already under a tremendous amount of stress because of human development and human activities. We can see the numbers of species that have disappeared over the past century, since the beginning of the 20th century until now. I don't know how many thousands of species would have disappeared because of human activity. And the numbers of the populations of various species have declined drastically. A century ago, I think 99% of the biomass of the, let's say, mammalian biomass on the planet was wild animals. Today 99% of the biomass is domestic animals like sheep and cattle and all that. So that's how drastically we have changed the uh, the environment, and we don't want to do that further. So introducing polar bears into Antarctica, first of all, we don't know if the polar bears can survive in that incredibly cold climate, and secondly, if they survive, then they could cause a significant disaster there. So something we don't want to do. Okay, same again, feminist slayer. Another thought experiment: what would how would Earth be affected if Titan, one of Saturn's moons, replaced our current moon? Okay, so the moon that we see in the sky, our moon, the satellite of the Earth, I think it's the fifth largest satellite, natural satellite in the solar system. I think the largest one is Ganymede, which is one of the moons of Jupiter, if I'm not mistaken. And it's known to have more water than we have on Earth. And when it comes to Titan, I think it could be the second or third largest satellite in the solar system, natural satellite. So Titan is a moon of Saturn. It's got an extremely thick atmosphere. It has all these exotic hydrocarbons in its atmosphere and on the surface in the form of lakes. It's got a very cold temperature. Uh, you have liquid methane, etc., on Titan, and it is larger in diameter and larger in mass compared to the Earth's moon. So let's say we conduct this thought experiment where we replace the Earth's moon with Titan, a larger satellite. What could happen? First of all, the straightforward impact on Earth is that there's going to be significantly stronger tidal activity on the planet. So we know tides, right? The ocean, it goes back and comes, the tides rise and fall. So the ocean recedes certain times of the day, it goes away, and the beach becomes longer, extended, and then certain times of the day the ocean it comes towards the shore, and the water level rises, and this is a periodic phenomenon that happens on a daily basis. So these are tides. Now let's say you have, and the tides happen because of the gravitational pull of the moon on the ocean of the on the oceans of the planet. So the Earth's oceans are always, the Earth, if you look at it sideways from far away, it will not look like a sphere, it will look like a squashed, it will look like an ellipse, almost an elliptical shape. It's there are bulges in the oceans, and these are because of the gravitational attraction, the gravitational pull of the moon. Now let's say you have a much larger moon, Titan, there, then the tides will be much stronger. So you're going to have disasters at the various seashores, coastal disasters. So much larger tides, which means that the water will come way further inland. It will destroy all the coastal infrastructure, coastal cities, coastal villages. It could cause a lot of devastation. So that's number one. That's the number one impact you will see. And humanity will have to somehow find ways to survive further inland and abandon all the coastal regions. That's number one. Secondly, it's going to cause tectonic activity, stronger tectonic activity on the planet, because the gravity of the moon affects the crust of the Earth as well. So if you have a much stronger, much larger moon, the gravity will be stronger, and it could cause more earthquakes, more volcanic activity, volcanism, etc. So that's another impact you would have. Then let's say you survive all that, then the night sky will look different. We see the moon as this whitish silvery object out there in the sky. Titan won't look like that. Titan would look reddish brown. It would look larger. The amount of reflectivity may be different from that of the moon. The moon's albedo is quite low. The moon, I think, reflects less than 10% of the light of the sun. Titan could reflect more, so you could have a much brighter night sky, and so on. And if Titan is at the distance that the current moon is, then there would be no mixing of atmospheres. But if Titan were closer, then there could be mixing of atmospheres, and that could poison the Earth's atmosphere. And then what happens on Titan? Titan is a moon, a satellite of Saturn. It's way far away from the sun, and that's why it's quite cold. Now, if you were to bring it into orbit around the Earth, then Titan would warm up because of the uh, heat of the sun, the radiation coming in from the sun, and that would completely change its entire chemistry, and it's the physics of its atmosphere, and the physics of its surface. So maybe its atmosphere would expand significantly more. A lot of the almost all, I would say all of the liquid methane and various hydrocarbons that are liquid in liquid form, in the form of lakes, etc., on the surface would all evaporate, which means that the atmosphere would expand significantly. Maybe it would lose a certain amount of the atmosphere. So a lot will change by bringing in Titan and replacing our current moon with Titan. So yeah, that's a thought experiment, interesting thought experiment. That's how you understand the various uh, principles of science. So, interesting question, yes? Rohan Bidi says, it is said that Jupiter is a failed star. Had it succeeded, how different would our solar system be? And would life evolve on Earth? Would Earth be in overlapping Goldilocks zones of the Sun and Jupiter? What's a Goldilocks zone, first of all? A Goldilocks zone is a certain distance away from your star where water can exist in liquid form. So in the solar system that we inhabit, the Goldilocks zone ranges. So the planets Earth and Venus are in the Goldilocks zone. So Earth and Venus have temperatures where liquid water can exist. Mars is slightly just way beyond the Goldilocks zone. Uh, in the past, I think liquid water did exist in Mars, so you could say Mars is also in the Goldilocks zone, kind of, but it's much colder. It's further away from the sun. So the Goldilocks zone is that region away from a star, in orbit around the star, any star, where liquid water can exist. That's Goldilocks zone. Now, is Jupiter a failed star? I wouldn't say Jupiter is a failed star. What is a failed star? You generally refer to brown dwarfs as failed stars. So, what does it mean for a star to fail? For a star to fail, it means that it doesn't have sufficient mass to ignite nuclear fusion reactions, a sustainable nuclear fusion reactions in its core. So if you look at the sun, our sun, it's this bright ball of light, right? Extremely bright. We are so far away from it, and yet it heats up the surface of the planet and causes all the weather and all that. And at the heart of the sun, there is this gigantic, massive nuclear fusion reaction. If you want to see what a nuclear fusion, what a hydrogen bomb looks like, look at the sun. That's an ongoing fusion reaction. So why is the sun able to sustain fusion? It's because it is massive enough to such that the pressure and temperature at its core is enough to have a sustained ongoing fusion reaction that's been going on for 4.5 billion years, 4.5+ billion years. So that's a successful star. It's able to sustain fusion, right? It's able to ignite, first of all, a nuclear fusion reaction, and it's able to sustain that because of the amount of mass it has, hydrogen mainly, a little bit of helium. Now, a failed star is a star which is a blob of gas, essentially, hydrogen gas, which doesn't have enough mass to ignite or to sustain nuclear fusion. So, the smallest mass that you need to ignite deuterium fusion, which is deuterium is a special form of hydrogen. Okay, hydrogen, what is hydrogen? It's an atom, right? It's a gas. The gas has atoms, and that the hydrogen atom is just a proton in the nucleus, then you have an electron going around it. You can look at it like that. Okay, it's not exactly like that, but yeah. So A hydrogen atom has a proton and an electron going around it. In deuterium, you have a proton plus a neutron in the nucleus, and you have one electron around it. So it's slightly different. It's a special kind of hydrogen. And there's tritium as well, which has two neutrons. So if you have an object, a gas giant, which has roughly 13 times the mass of Jupiter, then it has enough mass to ignite deuterium fusion reaction. And that's kind of, it's a reasonably cooled object. About 2000 Kelvin is the surface temperature of a brown dwarf. So it's kind of there is a fusion reaction going on in there, but it's not really hydrogen fusion, it's deuterium fusion. It's much cooler. And such objects are not very luminous. That's why they're called brown dwarfs. So the minimum mass for deuterium fusion is 13 times the mass of Jupiter, and the minimum mass for proper hydrogen fusion is about 75 to 80 times the mass of Jupiter. That is the lowest mass limit at which a red dwarf can exist. So such stars are called red dwarfs, and red dwarfs are much cooler than the sun because you can see that they are red, like the light behind me. And they are very long-lived stars. Their lifetime is typically of the order of trillions of years, so they will outlast. Well, the universe is 13.8 billion years old. So red dwarfs will essentially live forever. From if you look at the current scale, the current age of the universe. So that's what it is. Okay. So with that understood, Jupiter has is way too small to even ignite deuterium fusion. So Jupiter isn't a failed star. Jupiter is just a gas giant planet, the largest planet in our solar system. It simply doesn't have enough mass to ignite or sustain, to first ignite and then sustain any kind of nuclear fusion reaction, even deuterium fusion that you see in brown dwarfs. So it's not a failed star, but let's say you have a small star where Jupiter is currently. Okay, let's say you have a star. The smallest star you can imagine is a brown dwarf, which is 13 times the size of Jupiter, the mass of Jupiter. Well, what would happen then? Well, that star would be way too far away from us. So the dynamics of the solar system would be affected somewhat because of the larger mass of this object, which would cause, if you were to suddenly like do a thought experiment and replace Jupiter with a brown dwarf, what could happen? It would perturb the orbits of the various planets. It could cause certain planets to move, the orbits of certain planets to move, possibly. Some, planets could, over a long period of time, perhaps be thrown into different orbits or maybe even ejected, possibly depending on the mass of this object, of this brown dwarf, in orbit where Jupiter currently is. It would change overall the dynamics of the solar system, the orbital dynamics, and so on. Uh, what else would it do? It would not be warm enough to make much of a difference when it comes to the Goldilocks zone that Earth resides in. So Earth would not. Maybe it would certainly be visible, more visible than what Jupiter is. You can see Jupiter with the naked eye, but if you want to, but it's not that luminous because it is simply light that's reflected off Jupiter, sunlight that's reflected off Jupiter. But in the case of this hypothetical brown dwarf, it would have its own light, which would be more luminous than Jupiter, possibly, but it would not give us enough warmth that it would make much of a difference to us. What if you had a red dwarf there? Then it would possibly make a significantly larger difference to the solar system because of the much larger mass, and it would be much more luminous than a brown dwarf. But still, it may not really change much when it comes to the Goldilocks zone, because a red dwarf is way cooler than the sun, and it will be quite a distance away. So overall, that's what could happen. Life would not really evolve differently on Earth. Obviously the night sky would look different. You would have a bright object that isn't there right now. So yeah, it could change uh, the nocturnal cycles of animals, of birds, of insects, and all that. The circadian rhythms could change, perhaps that could be affected. uh, and yeah, the night won't be as bright, as dark as it is right now. So that is overall what could happen. I think there's this science fiction novel that I read a long time ago. I think, what was it, 2010 Odyssey 2 by Arthur C Clarke, one of the pioneers of science fiction and physics. And Yeah, I think this concept is examined over there. There's an alien civilization that ignites Jupiter somehow and sustains fusion there, and it kind of changes. I think that new star is called Lucifer in that science fiction novel. So yeah, interesting thought experiment. That's overall the scenario. Okay, nice roses. This is by Afridi Samiullah. What are biomarkers and how do we use biomarkers as for paleoclimatic analysis? From Pakistan. Nice to meet you, sir. Okay, what are biomarkers? So imagine biomarkers as tiny chemical clues left behind by life, plants, animals, etc., even microorganisms from a long time ago, millions of years ago, or at least hundreds of thousands of years ago. So these are tiny chemical clues that are left behind by life forms that existed on the planet a long, long time ago. And they are left behind in these little clues, these little chemical clues are found in various places. They're found in soil, they're found in rocks, okay, they're found in ice, they're found at the bottoms of lakes and oceans. And these clues are used by scientists to learn about what the earth was like a very long time ago. So what are the different kinds of biomarkers? You have lipids. Lipids are, you can think of them as fats of ancient organisms. So these lipids can stay preserved in ancient sediments and even in ice, and they can stay preserved for millions of years. So there is one, the lipids. Then you have isotopes. Like I said, these are special versions of atoms, carbon 14, etc. And these isotopes can tell you about temperatures and etc. that existed a long time ago, long time in the past. Then you have pollen and spores. So these are uh, tiny parts of plants. I mean, today you have pollen, right? Flowers have pollen on top of them, and that's part of of every plant's reproductory cycle. So pollen and spores. Spores, they are emitted by mushrooms and other organisms as well. So these are tiny parts of plants and various organisms that can show you what kind of plants were growing, what kinds of plants and organisms were growing in a specific area. And you can also tell what the climate was like depending on the type of pollen. And then you have pigments. Pigments are colors, right? So these are colors left behind by things like algae. You can even find pigments in ancient dinosaur fossils, which can actually tell you what the dinosaur feathers look like. Dinosaurs had feathers. Most dinosaurs had feathers. So you can sometimes find pigments embedded in dinosaur fossils, and that can tell you what the dinosaurs look like. So these pigments, forget about dinosaurs, pigments can be left behind by algae. So these pigments can tell us about various kinds of conditions in the past, what the water condition was like, what the conditions inside oceans were like, etc., what kind of biological activity was happening, and so on. So you can reconstruct past temperatures. You can determine the kind of changes that happened in vegetation and water. You can look at sediments at the bottoms of lakes and oceans, and that can tell you about various ancient environmental conditions like the temperature, then even soil pH, which is how acidic or alkaline the soil was, etc. So that's what biomarkers are, and we look for biomarkers in these various places like bottom sediments, fossils, even sediments at the bottom of lakes and oceans. You can look for biomarkers in ice cores. So you go to a glacier and you dig an ice core. You take ice cores out of the glacier at various depths below the surface. You will know what the conditions were like based on what kind of biomarkers you find, whether it's pollen or whether it's whatever else. You can even drill into the ice in Antarctica, where you have very pristine ice, and you will find biomarkers from there, and you can determine what happened at so and so year. Whether there was a volcanic eruption, whether the certain kinds of plants were more prevalent, and so on. So that's what you do. Marine sediments. You can look at you, you know sediments which you find in fossils. You can look at ice cores, and all of this help us understand ancient climatic conditions. So that's how biomarkers are an interesting and an important tool that help us understand the ancient climate of our planet. So yeah, that's what biomarkers are. Geopolitical dubase says, how do eyes differentiate colors? That's an interesting question. I mean, these are great questions to really understand conceptual science conceptually. So if you want to understand how eyes differentiate colors, eyes, you to understand the geometry of the eye, you to understand the optics of the eye, you to understand the biochemistry of the eye and the physics of the eye. There's so much that goes into this. And all eyes are different. I mean, the eyes of various species are quite different. So human eyes are quite different from cat eyes, from dog eyes, from horse eyes, goat eyes, bee eyes, insect eyes, and so I mean, whales, fish, very different. But how does it happen? So let's understand the structure of the eye. Okay, you have the cornea, which is the outer surface. You can think of it as the outer surface of the eye, the glassy outer surface. Then you have the lens, the pupil and the lens through which light goes in, and at the back of the eye you have something called the retina. Okay, now the retina. So what happens is light comes into the eye. Light is has various colors, various photons of various wavelengths. Okay, so this comes in through the cornea, goes in through the lens. It is collimated, let's say, through the lens, and focused onto the retina. So that's the optics. That's the optics of the eye, the geometry and the optics of the eye. So this retina is this layer at the back of the eye. And what does the retina contain? It contains what's called photoreceptor cells. And these cells come in two major categories: rods and cones. Okay, so the rod cells are responsible for vision in low light conditions. So when you are in low light conditions, you don't see color, do you? You only see gray, shades of gray. So the rod cells are responsible for vision in low light conditions, and they do not detect color. They are more sensitive to light, but they can't distinguish between the various wavelengths of light. So you can only see light and dark or shades of gray. So that's rods. Then you have cones. So the cone cells are responsible for color vision, and the cone cells, they function well. They function best in bright light. And at any given point in time, the light that's going into your eyes is activating the cones as well as the rods. But when it's bright light, you will your brain will you will perceive what the cone cells are telling you. In dark light, I mean, in low light conditions, you will perceive more of what the rod cells are telling you. Okay, now this cone cells, there are three types of cone cells, and each of these types of cone cells is sensitive to different wavelengths of light. So you have the short cone cells, S cones, M cones, and L cones: short, medium, long. So the S cones are, like they say, like it's clear from the name, short cones. They are sensitive to short wavelengths of light, which correspond to essentially blue light. Then you have medium cones, M cones, which are sensitive to medium wavelengths, which correspond to green light. And then you have the long cones, L cones, that are sensitive to red light. Okay, so when the light hits the retina, it is absorbed by photopigments inside the cones and the rods. Not the rods, the cones, because rods don't have they don't really have photopigments. So each type of cone cell absorbs light at different wavelengths, and this absorption of light causes a chemical change in these photopigments, and this chemical change generates electrical signals that are transmitted through the optic nerve, which crosses itself behind you. Okay, inside which it crosses like that, and then that signal goes into the brain, and then the brain's supercomputer processes these signals from different types of cone cells, and the way the relative activation of each type of cone determines the color that your brain perceives. So if the short, medium, and long SML cones are equally activated, then the brain will perceive that as white light. But if you have more S cones that are being activated, the brain will see that as blue light. If you have more M cones, medium cones activated, then the brain will see that as green light. And if you have predominant activation of L cones, then the brain will see that as red. So over here behind me, you will see red color. So that light is activating the L cones in your brain. Got it? And it's RGB, red, green, and blue. And if you are a designer, if you work with colors and all that, then you will know that all colors are a superposition, a combination of RGB. Okay, so that the same process happens in the brain. There is additive color mixing. So the different combinations of different wavelengths of light creates new colors. Okay, so red and green, if they combine, you get yellow. So that's how it happens. So that essentially is how the eyes sense colors. It's not just the eyes that are sensing colors, it's actually the brain that's sensing colors. The eyes are simply sending signals to the brain depending on what kind of cells in the retina are being activated, whether it is the rods or the cones. If it's rods, it's just shades of gray. If it's the cones, which kinds of cones are being activated, and what the additive color mixing of all of that is tells you what color that light is. So light is just wavelengths of photons. Okay, and the brain actually literally color codes all that to help us make sense of the external world. The external world is extremely complicated, but we see it as a simplified version of what it actually is. Okay, great question once again. Ayush says, why are water droplets in the air spherical in shape? I mean, that's such a simple phenomenon, but it is a brilliant question. These are the kinds of questions that help us understand the concepts, the basic concepts that underlie the world we live in, the basic physical concepts. Water droplets are spherical. Yes, we know that. I think we all know that. Water dripping from a faucet, from a tap. You see the water droplets are spherical. You can take a snapshot, a picture of that with your iPhone, with your phone, and you will see that the water droplet is spherical. And the smaller a droplet is, the more spherical it is. Okay, so why is it so? Why are water droplets spherical? There's a phenomenon called surface tension, which causes water droplets to be spherical. Okay, what is surface tension? Surface tension is a tendency, it is a property of all liquids. Okay, it's the tendency of liquid surfaces to shrink to the minimum surface area possible. Okay, this is a physical phenomenon. It's not chemistry, it's not biology, it's physics. So all water surfaces, all liquid surfaces have this tendency to shrink to the minimum surface area possible. And what's the minimum surface area possible? It's a spherical shape, isn't it? Right? And surface tension is the property that allows certain insects to walk on water. You must have seen that. you know Insects, what are they called? Wave riders, water riders, something, pond riders. There are certain insects that can walk on water. Leaves can float on water, for that's also because of surface tension. Razor blades can float on water. So all of this is surface tension. So in surface tension, what happens is that water molecules or liquid molecules are strongly attracted to each other, and at the surface, this creates a cohesive force which minimizes the surface area. And the sphere has the smallest surface area for any given volume. So this minimizes the energy state of the droplet. Now, when a droplet of water is falling, a drop of water is falling through the air, there is the internal pressure of the water in the droplet. It is balanced by surface tension forces acting equally in all directions. And you also have air resistance. So you also have the force of gravity, which is why when you have larger droplets of water, they get deformed when they are falling. They sometimes break up if the droplet is too large. When it breaks up, you will have smaller droplets that form, which become more spherical. So you have the force of gravity that's acting on the water droplet. It's causing the water droplet to fall towards the earth. Then you have the air resistance, which is acting against the direction, in the opposite direction of the fall, and so on. So when you have too large of a water droplet, it breaks up because of these forces. So the spherical shape is most noticeable in small droplets when water is falling. So that is essentially why water droplets are spherical. Excellent question. And that's how you understand basic physics concepts, which are the fundamental building blocks of our understanding of the world we inhabit. Next question is by RAMALAKSHMI. What is ASI, which is the next step of AGI? ASI, AGI. So AGI, most of us may perhaps have heard of it, artificial general intelligence. ASI is artificial super intelligence. So these are two very important concepts in the field of artificial intelligence. Okay, and artificial intelligence, AI, is all over the place right now. The past 2 3 years, it's erupted out of nowhere, emerged out of nowhere, because of the conditions that we have. Tremendous amounts of data at the disposal of companies and organizations, and also extremely powerful chips, GPUs, that can process the data. And that's how we have AI that's now a thing. And the next step is AGI, and the step after that is ASI. AGI is artificial general intelligence, and ASI is artificial super intelligence. So, what is AGI first of all? So, AGI, uh, AGI, as far as we know, has not yet happened. Artificial general intelligence. So, AGI is an AI system, is the state of an AI system, or an AI system can be said to have become an artificial general intelligence if it can understand and learn and apply its intelligence to solve any problem or any intellectual task that human beings can. Okay. So right now we have these narrow AI systems that are designed for specific tasks. So you have this chatbots and you have various other things, and you can ask questions and it will output text, and it looks like it's very intelligent and it's a very intelligent teacher, right? So that's a very specific narrow task, or set of tasks that these AI systems can do. So these are our current AI systems. So unlike these narrow AI systems designed for specific tasks, artificial general intelligent systems would have a human like ability to reason, to plan, to solve problems, to think abstractly, and to learn from experience across a wide range of domains. Okay, they'll be able to understand images, they'll be able to understand videos, they'll be able to understand deep concepts out of textbooks and books. And they'll be able to think and reason and plan and solve problems just the way humans do. Okay, and most likely AGI would probably be self-aware, most likely. I mean, that's typically what one believes. So that is AGI. It's a human-like intelligence, genuinely human-like intelligence, not the current text generators or image generators that we have. They just do it robotically. So that is AGI. AGI is different from that. It's a human-like intelligence, a human-level intelligence. Think of it as a 150 IQ person. What was Albert Einstein's IQ? I think it was in the 160s, right? So the most intelligent scientists that we can think of had IQs in the 150s and 160s, typically in the 160s range. 160s. Uh, so an AGI would be like that. IQ in the 150s or 160s, human equivalent. An ASI system, artificially super intelligent system, is a hypothetical future AI system that surpasses human intelligence and capabilities in virtually everything, all domains. So, this hypothetical form of artificial intelligence, AI, would be way more intelligent than the best human minds can possibly be in essentially any field, whether it is scientific creativity, scientific research, general wisdom, social skills, whatever, planning, problem solving, creativity, anything. It will be way more intelligent, vastly more intelligent than than the most intelligent human being that has ever existed. Okay, so AGI, it aims for human level intelligence across various tasks in various domains. ASI surpasses human intelligence, probably potentially by a gigantic margin. Okay, so if AGI represents is has an equivalent IQ, human equivalent IQ of 150 or 160, I think AGI would have an human equivalent IQ of 300 or 500, which is superhuman. It's not achievable humanly. So that's the incredible uh, gulf that will separate AGI from ASI. So right now, this is the state of, as far as we know, the state of AI research is that the immediate goal is AGI. It's not achieved as far as we know. Okay, we may not know everything, but as far as we know, AGI, artificial general intelligence, has still not been achieved. ASI is a next step after AGI. It is a more long term concept. AGI will match human capabilities, but it may not necessarily exceed human capabilities. ASI will exceed human capabilities in everything. So, AGI, once it happens, will revolutionize many industries, many aspects of life. It could lead to all kinds of unprecedented, potentially, you know, all kinds of unprecedented advances in technology, etc. But ASI could cause potentially unpredictable changes in society and technology. ASI could potentially take over humanity. Even AGI could potentially, uh, take over the world. So AGI is a field of development. Lots of organizations are working on AGI. ASI is currently a speculative, theoretical and speculative thing, whether it is feasible and what its potential impacts could be. So that's the difference between AGI, ASI. AGI could, you know, it could analyze tremendous amounts of scientific literature, and it could design experiments, run experiments. It could potentially make breakthrough discoveries in medicine, in physics, in engineering fields, etc. AGI can serve as a personalized tutor, a personalized teacher, who understands you very well, so it can adapt its teaching style to, and it can tailor its teaching style to each student's specific needs and requirements, intelligence level, uh, aptitude, and all of that. AGI can create works of art. Okay, it could create works of art, it could write novels, it could compose music, it could create all kinds of artworks in various styles. um, AGI could fluently translate any language, could fluently communicate in any language. It could translate in real time. It could even possibly learn, you know decipher ancient scripts, learn extinct languages from possibly limited data and all that. So that is what the kind of capabilities AGI could have. But artificial superintelligence could potentially solve problems we can't even imagine. We could achieve nuclear fusion on a tabletop, perhaps. It could potentially cure all diseases. It could potentially develop faster than light travel. It could potentially develop time travel. It could design materials with unimaginable properties. It could develop quantum computing systems in a small box, and so much more. So much more. So that's the difference between AGI and ASI. AGI could happen soon. ASI is more down the line. But it once AGI happens, ASI will certainly be the next next thing we want to work on. Right? Okay, Ritik Pawar says, what are your thoughts on the recent developments at OpenAI, specifically OpenAI appointing former NSA, National Security Agency US Director Paul Nakasone to their board? Ilya Sutskever, one of the genius scientists and co-founders of OpenAI, leaving the company to start a new venture focused on building artificial superintelligence (ASI), which he claims is within reach. Do these events suggest that OpenAI may have internally achieved artificial general intelligence (AGI), or that significant achievements are happening behind the scenes? You know what? Look, whenever see um, civilizational progress always depends on technology. And humanity throughout history has had competing cultures, civilizations, empires, etc. And the ones that succeed are the ones that develop the best technologies and deploy the best technologies. That's always been the pattern throughout history. So and when new technologies are developed, they are invariably 100 times out of 100 first used by governments and militaries. That is just the way it is. And when you develop new technologies, you hide that. You don't let the world know what your capabilities are. So when you have all these companies that are American companies that are developing the next big thing in technology, artificial intelligence systems, AI systems, well, what we can see, what is being shown to us is going to be simply the tip of the iceberg. There's a lot more happening that is secret. And the US government obviously will want to take first would want to have first use of all these technologies, and it would want the most important bits of the technologies to remain under wraps. And the fact that the former NSA director Paul Nakasone, a former US general and former director of the National Security Agency, Paul Nakasone, he is now on board OpenAI. It tells you that the US government is very much involved in this matter. And what we are being shown is simply a fraction of the real capabilities of OpenAI. So I am only speculating, but it could mean that they have achieved AGI, artificial general intelligence, or maybe more than that. Who knows? And that gives that government, that nation, incredible advantages over other nations. Nuclear survivability, nuclear targeting. I mean, there are all these military applications of AI. Okay. Now, nuclear exchanges are a nightmare scenario which will lead to the extinction of humankind. But what if AI can find solutions that will allow you to not only survive a first strike, but to unleash a second strike that will, you know, help you win, and it will defeat the opponent. So we'll talk about US and Russia, obviously. So yes, AI could do that. It could find solutions that the human mind can't find. So yeah, it's possible they may have achieved AGI or maybe something beyond that. And the second point is that you're raising, Ilya Sutskever has left OpenAI and he's started a new venture focused on a single agenda, building artificial super intelligence, ASI. He claims it's within reach. It also kind of hints that they may have already cracked the AGI boundary. So I think in November or something last year, 2023, there was a coup in OpenAI, and Sam Altman was ousted, and he very quickly returned. And Ilya Sutskever was then, after a few months, he was made to leave, let's say. So it tells you that certain forces are at play behind the scenes, and OpenAI has a certain mission. See, the stated mission is to develop AI systems that will benefit humanity. But that's just the stated mission. That's just words, slogans. There could be a different mission, and that's why Nakasona is on board probably. And that's why Ilya Sutskever, who tried to oust Sam Altman, has now had to leave, and he is obviously one of the pioneers in AI. So he's now starting a new venture. He has started a new venture which will focus on ASI, which he claims is within reach, which would imply that AGI may have possibly been achieved somewhere, maybe at OpenAI. So yes, I agree overall with the speculation that it could possibly already have happened. Okay, Rohan Bidi says, how does superconductivity work, and does it have any practical applications for daily usage? Superconductivity. How do I explain superconductivity? Let me not go into the quantum mechanics of superconductivity because that would be counterproductive. Uh, you've been to water parks, right? Water parks. In water parks, you have these big slides that twist and turn, and you slide down these water slides. Hmm? And there's water running down the slides, and these slides go in spirals, or sometimes they go in zigzag shapes and all that. And you start at the top and you eventually end up in a pool of water after going through the slide, right? So that's what you have in water parks. Now when you are going down this complicated zigzag slide, you will see that your speed will keep varying, and you will sometimes experience friction at the edges of the slide when you're turning, and you'll slow down at places, and you'll speed up at places, and so on. So you will experience friction, and you will experience slowing down in various parts of the slide. Now, that is similar to electrical current passing through a wire. In a wire, when electricity passes through a wire, it encounters what we call resistance. Every conducting material has a certain amount of resistance to electricity, and it's like you passing through going down the slide and encountering all these obstacles, and slowing down and encountering resistance. That's kind of like what electricity experiences when it passes through an electrical conductor in an electrical wire. And because of this resistance, some of the energy is converted, it is wasted, it is converted into heat energy, it's converted into heat. So you have transmission losses because of this. Now imagine you have this slide, which is a magical slide in which you encounter no resistance whatsoever, and even the water is a special water, and you just zip through it, woof, at the maximum possible speed. So that's kind of like superconductivity. Okay, so in superconductivity, what happens is that there is essentially zero electrical resistance, and even magnetic field lines are ejected out of the material, kind of Meissner effect. So that's how I could give you an analogy of what superconductivity is. It's because of Cooper pairs, electrons behaving in certain ways in certain materials below a certain temperature, the critical temperature of the material, and so on. So that is essentially what superconductivity is. And superconductivity is like a magical effect, essentially, and it obviously has practical applications. I can think of a few applications. Magnetic resonance imaging. You've heard of MRI machines. You go to a hospital with a fracture or something or whatever, then you're going to be put into an MRI machine. And so what happens is that in MRI machines you have superconducting magnets that generate strong and stable magnetic fields, which allow the machine to create detailed images of the interior of the human body. So MRI machines, then you have magnetic levitation, maglev trains. These trains, they use superconducting conducting magnets to float above the tracks. So maglev trains, they don't touch the tracks, they float above the tracks. And this is done with the help of by using superconducting magnets. So there's essentially zero friction, and you have very high speed travel in maglev trains. Then you have particle accelerators. So you must have heard of the Large Hadron Collider outside of Geneva, Switzerland, LHC. So in these, it's the biggest particle accelerator that we currently have on the planet. So in these particle accelerators, superconducting materials are used in the construction of these particle accelerators, and they create extremely powerful magnetic fields which are necessary for accelerating particles and confining particles at high speeds. Then you can have superconducting cables that transmit electricity over very large distances with very little energy loss compared to standard copper cables or aluminum cables. And then superconducting we can also have superconducting materials can be used in the development of qubits inside quantum computers. These qubits are the quantum analog of your classical bits, ones and zeros, and these qubits have states of superposition, and they can perform very complicated calculations at speeds that classical computers simply cannot attain. So these are some of the uh, applications of superconductivity, of superconducting conducting materials in the real world, and some of these can have daily usage. The magnetic levitation maglev trains certainly have daily usage. Transmission cables, superconducting transmission cables certainly have daily usage, and so on. MRI machines, daily usage. So there is there are applications of superconductivity in the real world outside of the specialized scientific and engineering domains. Somijit Mukherjee says, what's the next big invention in this century? So we are already in the age of AI. We're already in the age of AI. So I would not say that AI is the next big invention. AGI is the next stage. Then you have ASI, like we spoke about. Uh, so let's not talk about artificial intelligence. What's the next big invention? Human progress depends on energy. Energy. Everything in human life, in human civilization, depends on energy, the availability and accessibility of energy, storage of energy, and expenditure of energy. Every human activity is involves the expenditure of some form of energy. In the very primitive era, when we were in the Stone Age, energy was muscular energy. So you eat food, and the energy that comes out of it was used for muscular activities, lifting stones or whatever. So that was the expenditure of energy in the Stone Age. Then later on, you had when you construct bridges, etc., you are spending energy. When you are constructing walls and buildings, you are spending energy once again over there. So that is expenditure of energy. Then when you travel, when you have horses, when you travel on horses and ox carts, there's the expenditure of that animal's energy. Then obviously you have vehicles, combustion engines, you're spending expending chemical energy stored in the bonds of the hydrocarbons, chemical bonds of the hydrocarbons, which is converted into heat and all that. Then you have rockets and you have electricity and all that. So it's all the expenditure of energy. All human activity depends on the expenditure of energy. So I think the next big invention in this century is gonna be energy storage and expenditure. Imagine, right now we have electric cars, right? Electric cars have these gigantic lithium ion batteries at the base of the car, which give the car tremendous stability. It lowers the center of gravity and also provides the power that the car needs, right, to move. Lithium ion batteries, big, massive batteries. Imagine a coin sized battery that gives you the same power. And imagine that little coin-sized battery gives you the same power as that giant lithium-ion battery, but it lasts 20 years. It can store enough charge to give you sufficient output for 20 years. That is, I think, the next big invention in the century. That is kind of in the realm of science fiction, but yeah, that could be a revolutionary invention. I think some Chinese scientists have already developed a nuclear battery, a really small SD card sized nuclear battery, which can charge your phone for 20 or 50 years or something. But that's a very small amount of charge. It can charge a phone, a small device. Imagine a coin sized battery that can charge a car, that can power a car for 20 years. I think that's the kind of next big invention we're going to get in the century, but it's not going to happen soon. And when it happens, it will be hidden from view and it will be used in militaries first. But that could be the next big invention in the century. Something of that sort. Something that is kind of not really thought about or spoken about. And of course, nuclear fusion, if it happens, sustainable, controllable nuclear fusion. First of all, it will happen in these big, gigantic machines called tokamaks or whatever it is, or something like a tokamak. But eventually, if you can have a tabletop device that can sustain a controlled nuclear fusion reaction, that could be a significant breakthrough, a revolutionary breakthrough. So, yeah, I think the next big inventions are going to involve energy storage and transmission and significant orders of magnitude uh, change, improvement in what we currently can achieve. I think that could be the real next big invention in the century. Geopolitical Dubey says we can see water, we can see fire, we can see smoke, we can even see space. Why can't we see air? Why is air and why is wind invisible? Why can we just feel air and wind? Why can we not see it? Once again, great question. Great question. These are questions that go to the heart of science, of understanding the world we inhabit. So, yes, you are right. Air is invisible to the human eye. It is invisible because of its physical properties and the way light interacts with it. Okay. So, I am in this room here. Obviously, there's air around me, but it's invisible. It's transparent, essentially, right? So, why is it transparent? So, first, let's understand what is air composed of? What is the composition of air? So, air is composed mainly of nitrogen and oxygen. About 78, 79% nitrogen, about 20, 21% oxygen. And then there are small trace amounts of other gases like carbon dioxide and water vapor and argon and whatnot. So that is essentially air, mainly nitrogen and oxygen, little trace amounts of carbon dioxide, water vapor, etc. And these gases are made up of molecules. These molecules are obviously extremely small and they are spaced far apart relative to their size. So over here in this volume between my hands, there's a tremendous amount of air molecules. But if you go to the atomic molecular domain, then you will see that these are extremely small and they are spaced really far apart compared to the actual size of each molecule. Okay, so very diffuse gases. Now, these molecules of gas in the air, they do not absorb visible light significantly. So when the light passes through the air, it essentially goes through mostly without being absorbed and without being scattered. So that is one reason why air is transparent, and that's why we cannot see it. So absorption, there's almost no absorption of light. Scattering. What about scattering? So air molecules do scatter light, but the scattering is extremely weak. What is the scattering called? It's called Rayleigh scattering. Rayleigh. Rayleigh scattering. And you can't notice it over here, but you can notice it if you look up into the sky in daytime. You will see that the sky is blue. Why is it blue? It's because of Rayleigh scattering. So this phenomenon, Rayleigh scattering, is responsible for the blue color of the sky. It's also responsible for the yellowish, reddish, orangish color of the sky when the sun is setting far at the horizon. So up there it's blue, and at the horizon, when the sun is setting or when it's rising, you will see the sky is going to be yellowish or reddish or orangish. So that is because of Rayleigh scattering. So light is scattered, but it's scattered very weakly. But it's not enough. The scattering is not enough to make air visible in the way that smoke is visible or fog is visible. So smoke and fog, they scatter way more light than the actual molecules of air itself. So the density of air is very low. So compared to a liquid, okay, you're talking about liquids, right? So so when it comes to liquids, liquids are much denser than water, than air. Water is much denser than air. Solid substances are much denser than air. So that's why they have different phenomena, and they actually uh, do become visible, right? So water is visible because it is a much higher density than air. The water molecules are packed closely together, and that allows the water molecules to scatter and reflect light much more strongly than air molecules. Smoke is visible because it has solid and liquid particles suspended in air, and these particles are dense and they are numerous enough to scatter and reflect light. Why is fire visible? Why is fire visible? Fire is visible because of incandescent particles and gases that are part of the flame, and they emit light because of the extremely high temperatures. So these are the reasons why fire and water and other substances are visible, but air is not visible. We obviously do feel the air. One of the reasons we feel air is because of the air pressure. There's a tremendous amount of pressure that the atmosphere of the planet exerts on us. You standing somewhere, you're going to have 100 kilometers of air on top of your head, so it's gonna exert some pressure, right? So there is air pressure, and moving air also exerts pressure on your skin, and it causes sensations. First of all, because of the pressure it causes, and also because of the temperature change. So these are the reasons why you can sense air, you can sense wind, but you can't see it. And that's why air is more or less invisible, except when you see it up high in the sky, when there's 100 plus kilometers of air between you and outer space, and you can see it. You can see the color of the air, which is blue, or it's yellowish, reddish in the evenings and early mornings. Summit statement says, if humans and present day apes share a common ancestry, why don't apes exhibit logical thinking and develop like humans? What enabled humans to become civilized? Well, that's a good question. So we know that apes and humans share a common ancestry. The last common ancestor of humans and chimpanzees, I think the split happened what, 2 to 4 million years before today, roughly. And then there was a common ancestor of humans, chimpanzees, and gorillas that existed around roughly, I think, 8 million years before today. Don't quote me on that. I could be off by a million or 2 years, but you get the point, right? We had common ancestors. So why don't apes exhibit the same kind of thinking, etc., that we do? It's because we evolved differently. Think about dogs and bears. You look at a dog's face, you can look at a bear's face, quite similar, right? They would at some point in time have had uh, common ancestors, but they have different levels of intelligence. I know bears are also very intelligent. They're almost like gigantic dogs. But let me give a better example. Uh, Consider the difference between a chimpanzee and a lower monkey, like a slow loris or something. Significant difference in the level of intelligence. It's because each species evolved separately and in different ways. In the past, You did not have air travel, train travel, all that stuff. So you could not travel long distances. It was very hard to travel long distances on foot. So when populations got split off for whatever reason, they evolved for millions of years separately. And wherever you evolve, there are different sets of parameters, different sets of climatic and geographical conditions, different kinds of foods that's available, and so on. And because of that, the species evolved differently and acquired different characteristics. And I think it was because of whatever accident of nature that we evolved the way we did. Our brains became much larger. We became mostly bipedal. Chimpanzees and gorillas can still crouch and walk on all fours. We are exclusively bipedal creatures. And when you become bipedal and you stand up on 2 feet, then your eyes are much higher from the ground than, for example, that of a cat or a dog. I mean, if there are videos on YouTube. People, some people attach GoPro cameras or small cameras to the collars of cats and all, and then you can see the world from their level, and you can see how much closer to the ground it is, and how less information is accessible to the eyes at that level. But when you're higher up, I mean, think of it. You go to the top of a hundred story building and see how far you can see and how much information is available to your brain just through your eyes. So the higher you are, the more information is available, and the more your brain needs to develop to be able to process that information in real time. So because we became bipedal, exclusively bipedal, our brains had to adapt to this postural change and grow larger to be able to absorb and process more information, much more information in real time. Chimpanzees can walk on 2 feet, but they often walk on all fours, etc. Right? And so, because of the different ways in which we evolved, we acquired different levels of intellectual abilities and different levels of intelligence. So I think what enabled humans to become civilized, first of all, we became more intelligent. Our brains, the size of our brain, the volume of our brainial capacity increased because of our bipedal stature, the bipedal posture of ours. And then because the brain had expanded, it had become capable of absorbing and processing more data, more information. It also manifested itself in other ways. We became more social, communicative. We developed language. We developed societies, cooperation, eventually division of labor. Then we eventually discovered fire, and so on and so forth. So these are the processes and agriculture, and then civilization. So these are the processes by which we became way more civilized than apes. And that's essentially how it is. That's all about evolution. ED Guru Prasad says, our brain doesn't use mathematics. Still, how is it able to do a lot of essential calculations? Right. You know, when we talk about physics, our brains understand physics. You know, you can solve Newton's equations of motion for projectile motion. You throw a projectile, you can derive the equation for the projectile motion. It will go in a parabolic path, and it will reach a certain maximum height, and then it will once again fall at a certain distance from which you threw it, depending on the angle and the speed of the thing and the mass of the object. You can calculate all of this using Newton's equations, and derive the equations for parabolic motion, and you can solve that for the size of your projectile, the speed at which you throw it, the angle at which you throw relative to earth's surface, etc. So you can do it like that. But when you play a game, when you play, let's say, whatever, cricket, whatever, you throw a ball, you don't have to do any calculations. You just intuitively know how high the ball will go and where it's going to touch the ground, and you can catch it before it does that, right? So you just know it intuitively. What about, okay, so we know that intuitively because we've got massive brains compared to other animals. What about dogs? You take a ball, you throw it, your dog's gonna go after the ball, is gonna know exactly where the ball is gonna touch the ground, is gonna jump, leap up in the air, and catch the ball midair before it touches the ground. How does a dog know this physics? Did the dog solve Newton's equations of motion, or parabolic projectile motion? How did the dog know this? And when we walk on 2 feet, we know exactly what the balance of all the forces is. We are being acted upon by multiple forces at any given point in time. The force of gravity, and whatever the wind and atmospheric pressure and so much more. And we are walking, which is an unstable movement, but we are able to balance it in real time without even thinking about it. And the same goes for other animals. How do we do it? We are performing calculations in real time. Are we, or are we not? What is the deal? So there's clearly a tremendous amount of understanding that the brain has. So how does it happen is the question. So look, when it comes to the human brain, we have about what's the number? How many neurons? Between 80 and 90 billion neurons. Okay, we have between 80 and 90 billion neurons. That is one with nine zeros after it. And you multiply that by 80 or 90. That's the number of neurons you have in the brain. And these neurons are all interconnected. They communicate through synapses. And each individual neuron can form thousands, tens of thousands of synaptic connections. And this creates an incredibly complicated, incredibly vast and complex network of neurons. And these neurons, they communicate with each other via electrical impulses and chemical signals, neurotransmitters, all that. And this neural activity, this incredibly complicated, complex neural activity, allows for the rapid transmission and processing of various kinds of information. So that is one way the brain works. That is kind of the way the brain works. And the brain, it doesn't it processes information in parallel. It doesn't do it sequentially. When you have a computer program, a standard computer program, it runs sequentially, but in a standard regular computer. But when it comes to the brain, information is being processed in parallel. You have different section, areas of the brain that specialize in various kinds of information and data and perception, and they are all communicating with each other and processing information in various parts of the brain in parallel. So multiple processes happen inside the brain simultaneously. So there's a very efficient and very rapid handling of sensory input, also motor control, cognitive tasks, throwing, catching, walking, speaking, cognitive tasks, motor control, the way we control our limbs and so on. And then the brain, it excels at recognizing patterns. It can recognize shapes, it can recognize faces, it can recognize sounds, it can recognize various other stimuli by comparing the incoming sensory data. Okay, the sound, the shape, the face, it can compare that incoming data with stored representations of data, memories. So memories are complex packets of data, you could say, that are stored in the brain. And then the brain has an ability to reorganize itself. It's called neuroplasticity. It reorganizes itself simply by forming new neural connections. So this property, neuroplasticity, allows the brain to adapt to new information. It allows the brain to adapt to new experiences. It can even allow the brain to recover from injuries and give you a reasonably similar lifestyle before and after, let's say, some kind of injury on the brain, right? So that's how the brain works. And through this learning, you could call it reinforcement learning, experience, etc., the brain refines its processing capabilities. And reinforcement learning it involves practice, repetition, and these activities, they strengthen the various pathways in the brain, neural pathways, which makes the execution of various kinds of tasks more efficient over time. And it can, I suppose, the brain can also perform basic arithmetic computations, maybe intuitively. It can quickly estimate quantities and recognize patterns and perform simple addition, subtractions, probably without conscious effort, and so on. And then the brain is for more complex problems and operations, the brain is very much capable of logical reasoning. It's obviously this memory retrieval, this approximation. When you see a mountain compared to a stone, you immediately know that the mountain is way more massive than a stone. So all of that logical reasoning, approximation is there. And the brain breaks down complex problems into manageable parts and uses the strategies it has learned over time to find solutions. And this happens mostly subconsciously. It is said that only 1% of the mind, it is said, I don't know how accurate that is, but roughly 1% of the mind is conscious, 99% is subconscious. So the subconscious is where all the processing happens without us knowing about it, and so on. So that's kind of how the brain operates. It doesn't use mathematics. It may use, uh, you know, but it's still able to do all these essential and very complicated calculations in real time without us even knowing that all of this is happening. We don't realize it. We don't cognitively sense the calculations and all pattern recognition, all that happening. It just happens. So our conscious mind is unaware of the subconscious processing that's happening, and that's the way the brain is organized, and that's how it functions. And we know actually next to nothing about how the brain really functions. But yeah, over time we understand more, I guess. Malik Sayed says everything around us is made up of atoms, and as we know, yes. Does it mean that our brain, and this means that our brain is also made up of atoms, and our brain is able to think and it is conscious? We know that, yes. Doesn't that tell us that atoms can think? Even neurochemical, okay, neurochemicals, which neurochemical processes that happen in the brain and are subatomically made up of atoms. Is this argument correct to say that atoms can think? Okay, so we know the brain is made up of atoms, molecules, and further complex substances like amino acids and proteins and neurons and synapses and all of that. So there's a lot of neurochemistry in there. There's chemistry, there's biology, and at the fundamental, deeper level, there is physics, quantum physics at the end of at the bottom of it all of that. And obviously, everything is made up of atoms. So we know that we are conscious and we can think and we can perceive the world and all that. So does it mean that atoms can think? That is the fundamental question you're asking. So think about it like this. What do I have here? It's a rock. It's made of atoms. I have more rocks. I show you a white rock. There's a blue rock here. There's a blackish, dark purple rock here. There's a yellowish, whitish rock here. So these are all rocks. They're also made of atoms. They're actually crystals, crystalline objects. They're also made of atoms. Why don't they think? Why don't they think? Why doesn't my shirt collar think? Why doesn't my microphone think? Why don't these books think? Why doesn't that wooden rhinoceros behind me? Why doesn't it think? Why doesn't that deer think? That wooden deer, and so on. Why don't they think? They're also made of atoms. So clearly, it tells you that this over here, the brain, is a very special configuration of atoms. Nothing else in the universe is capable of thinking or being conscious. Brains are. Human brain, cat brain, monkey brain, bee brain, all have different levels of consciousness. But we know that they're conscious, and we know that there's some thought going on in there. Right? So it's not atoms that think, it is very special configurations of atoms that seem to be the seat of consciousness and thinking. How does it work? We don't know. We don't know. We simply do not understand consciousness from a scientific perspective, and from any other perspective also. We don't understand. I mean, in philosophy, spirituality, religion, there are various schools of thought as to how consciousness happens and all that. There's the concept of the soul, etc. But we're talking about science over here. We're talking science, observable phenomena, physical objects only. So from the perspective of observable phenomena and physical objects only, we only know that there's a brain in here, and it seems to be the seat of consciousness and the seat of thought. And we know that if somebody gets brain injured or something, the consciousness disappears. I mean, if somebody unfortunately gets shot in the head, consciousness goes, and thoughts go, and life itself goes. So clearly, the brain is the seat of consciousness and thought. It's made of atoms, but there's so many different configurations of atoms, and they don't think. Only the brain thinks. So it seems to be that a very special configuration of atoms is the cause for consciousness and thinking, or maybe it is the seat of consciousness and thinking. But how does it happen? Where does consciousness arise from? Is it an emergent phenomenon? Is it a different kind of phenomenon? Is it something that permeates the universe? We have absolutely no idea. We don't even have a physical scientific definition of consciousness. We don't have that also. We don't even have that. We don't even have a definition in science, whether it is physics, chemistry, biology, neuroscience, whatever. We don't have a definition of consciousness. So we can't answer the question. Right now, The answer to your question is beyond the reach of science. But it's a great question that you're asking, because it helps you understand conceptually what these phenomena are, because we have atoms everywhere, different configurations of atoms, rocks, books, statues, objects, whatever. They don't think. Why? What is special about this? Something about the brain is special, but what is it? We don't quite know, and we're trying to figure it out. Swapnil says, how did the progression from mathematics to physics to chemistry to biology unfold in the universe, demonstrating a seamless continuum? So, at the beginning of it all, as far as we know, there was the initial singularity of the universe, the Big Bang singularity or near singularity. We don't quite know whether it was a genuine singularity or a near singularity. If you look at loop quantum gravity, there is no singularity. There's only uh, the unit, which is 10 raised to minus 98 or something, times the Planck scale, I think, Planck length. So, yeah, Planck length or centimeter or meter, I'm not sure, but yeah, it's extremely, extremely small. So we had, let's say, a Big Bang singularity, and then something caused the universe to expand, space time to expand. And initially, you had a single unified force, as far as the best we can understand, a single unified force in which described everything in the universe. So the initial state of the universe was extremely dense, extremely hot, and you had all kinds of energy and particles, everything in that hot dense soup, like you say in the cliche. So, and you had a single force, and then you, as the universe expanded and started cooling, you had symmetry breaking, and the various forces emerged out of this. They broke off from the unified force, whether it is gravity or the electromagnetic force or the strong nuclear force or the weak nuclear force. They all broke off, they all separated at different energy scales, temperature scales, and it all obeyed the laws of physics, which are described by mathematics. So think of it like somebody outside the universe wrote a big program which encodes the laws of the universe. So the program was written in the language of mathematics. Essentially, that's how you can understand mathematics. Mathematics describes the regularities and patterns that underlie the universe. So that's mathematics, and that's what underlies everything. And then you had physics, which describes the actual laws, the actual objects, and everything that's inside the universe. And then you had expansion of the universe, inflation, superluminal expansion. And then as the universe cooled down, you had the formation of the first atoms, then the formation of the first stars, then galaxies. Dark matter, dark energy are somewhere in there. We don't know what their actual role is, but so the universe was very, 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 very hot initially, and then it started expanding and cooling, and the stars, etc., formed. Galaxies eventually started forming, and there was a time in the universe's ancient history when the average temperature of the universe was the average temperature that we have on Earth today. So it would have been very easy for life to form anywhere in the universe at the time. So what you have is, you have mathematics, you have physics, and then through physics you have chemistry, because you have molecules combining together in through processes that we call chemical processes, and the formation of various complicated molecules like amino acids, which are the basis of proteins and all. So it all happened in a systematic, uh, continuous manner, logical manner, and eventually you had life. We don't quite know how life happened, but it happened at lower temperature scales, clearly. I mean, the kind of life we understand. There could be other forms of life that we're not aware of, that we can't perhaps even imagine, perhaps. But the kind of life that we are familiar with, it would have emerged at much lower temperature scales. And how did DNA molecules come into existence? We don't quite know. Uh, it's possible the DNA molecules could have first formed in the universe when the average temperature of the entire universe was about the average room temperature on Earth today, possibly. You know, and then maybe they drifted across the universe on space dust and space rocks, etc., and the seeded life in various parts of the universe. That's a possibility, but we have zero evidence of that. So it's just a hypothesis. It's just speculation. But that's overall how it would have happened. And obviously, everything, the underlying everything, you have the laws of physics, which are described by mathematics. So the laws of biology are described at the foundation of biology. We have the laws of chemistry, chemical reactions. And chemical reactions, to understand that, you have to understand quantum physics and all and various other forms, other fields of physics. And underlying physics, you have mathematics. So that's the connection between everything. Asha Kashyap says, what's dark matter? Dark matter. Okay, dark matter is. So first of all, how did the idea of dark matter come about? It came about through observational evidence. In the early 20th century, it was discovered that the Milky Way was not the universe. We had faraway objects way beyond the Milky Way, stars, galaxies, etc., mainly galaxies. And then it was discovered that the galaxies are receding away from us. They're moving further and further away from us. So there's redshift and all that we discovered. And then we discovered that when we observe galaxies, when we take spectrometric measurements of the light coming from the galaxies, then you will find that one end of the galaxy, let's say it's a spiral galaxy, one end of the galaxy, the light coming from there will be red shifted and one end will be blue shifted. So we know that galaxies are rotating. And based on the redshift and blue shift, we can determine at what speed the galaxies are rotating. And then you can calculate the amount of mass inside a galaxy by computing its luminosity. So we know how much mass is in a galaxy. We know at what speed it's rotating. And then you find that the rotation of speed of the galaxies that we observe, it doesn't match the amount of matter the galaxy contains. It's rotating way faster. Why is that? That can only be explained by saying that the galaxy has way more mass, but we can't see it. And we find that in most galaxies. These are called rotation curves. We find that galaxies rotate faster than they should be rotating based on how much the amount of matter we see. So there is clearly some kind of unseen matter inside these galaxies, or that's part of the galaxy, but we can't see it. And that's how the concept of dark matter came into existence. So we now know that most galaxies have this phenomenon. And if we add everything up, we find that about 24% of the mass energy of the universe, roughly 24-25%, is made of dark matter. Only 4 or 5% is visible matter. Everything we see in the universe, stars, galaxies, nebulae, whatever, dust clouds, everything that is luminous makes up only about 5% of the mass energy of the universe. About 25%, roughly, give or take, is dark matter, and about 70% is something called dark energy, which is even more mysterious. But anyhow, that is what dark matter is, and there are lots of theories about what dark matter could actually be. It could be some class of particles. There is modified Newtonian dynamics also, MOND, which kind of gives you a solution for this without having to postulate or theorize that there are classes of particles out there, dark particles. But if you set aside MOND, the theories are that dark matter could be various classes of particles. Either particles that are purely gravitating in nature, purely gravitational, they only interact via gravity, not via the electromagnetic force. Or maybe these particles could also have the weak interaction. So there are lots of different classes of particles that have been proposed, like WIMPs and machos and axions and strangelets, primordial black holes, stable quantized bound states of primordial black holes, much more. So that is what we understand of dark matter. We have zero observational evidence thus far of any of these particles. There are certain experiments that are running, and some experiments give you some telltale signs of something out there, but it is still under dispute. So we still don't have any answers. So that is essentially what dark matter is. Okay, Ashakasha once again says, are wormholes real or are they mere theories? Look, we have never observed a wormhole. So wormholes are a certain class of solutions of the Einstein field equations of general relativity. Okay, so you solve these equations, these field equations, and some of the solutions are wormhole solutions. So wormholes are essentially shortcuts between two very far apart regions of space time. It's like, the classical cliche is that you take a sheet of paper, bend it in two, and you poke a hole through that. That's like kind of an analogy for a wormhole. So it is a valid class of equations of the Einstein field equations of general relativity, but we have never actually observed a wormhole. So it is a theoretically valid solution, but it has never been observed thus far. But it's possible that the objects we observe, some of them could be wormholes. So we know that at the center of most galaxies, you have supermassive black holes. We haven't actually gone there and measured the properties of the black hole. We have the Event Horizon Telescope that has taken snapshots of two black holes. One is the Sagittarius A star, supermassive black hole at the center of our galaxy, and there's another one as well, much further away. And we know that the snapshot that we get of the black hole, it actually matches exactly what general relativity tells us. But there are these supermassive objects at the centers of most galaxies that we know of, and it's possible that some of those could actually be wormholes, but we don't quite know. So we don't know for sure. We don't have unambiguous observational evidence that so and so object is actually a wormhole, not a black hole. We don't know, but they could exist. They could certainly very much exist according to the laws of physics, according to general relativity. They should exist, but we haven't observed them yet. So thus far, they are theoretical objects, but someday we may find them. All right. Rohan Bidi says, in relativity, gravity is a result of mass in the fabric of space. Relativity also says that mass and energy are two forms of the same thing. Then does energy also generate gravity? Your answer is, sir, yes. Energy does indeed generate gravity according to Einstein's theory of general relativity. And this is a profound and very important insight. Okay, so we know the wonderfully famous equation E equals mc squared, equivalence of mass and energy. That is Einstein's famous equation, which tells us that mass and energy are equivalent and interchangeable. Okay, so in general relativity, the presence of mass curves space time, and this curvature is what we experience as gravity. Now, since mass and energy are equivalent, energy also curves space time and generates a gravitational field. And this applies to all forms of energy, like the kinetic energy of moving objects, potential energy in fields, electromagnetic energy, and even the energy of the gravitational fields themselves. So, the mathematical formulation of general relativity. So, in the mathematical formulation of general relativity, the source of gravity is described by the stress energy tensor, and this stress energy tensor includes contributions from mass as well as energy. So the answer is yes. So in most let's say everyday situations, the gravitational effect of energy is negligible compared to that of mass, but it does become significant in extreme asymptotic scenarios, like for example the conditions that we had in the early universe when energy densities were extremely high. So there you would actually noticeably see this. Then when it comes to black holes, where the curvature of space time is extreme, and when it comes to the large scale structure of the universe, where the energy, that is dark energy, plays a crucial role. So yes, I agree that that mass and energy are two forms of the same thing, and energy does indeed, let's say, like you say, generate gravity. Right, it does actually contribute to gravity, what we perceive as gravity. Potato Praiser says, what will happen if strange matter comes into contact with a black hole? Will the black hole turn into strange matter? All right, that is a complicated question. Let's understand what strange matter is. What is strange matter? So, to understand that, um, how do I approach this? Okay, you may have heard of stars going supernova. Stars explode, right? And that is caused by the collapse of a star upon itself, and then there's a process that also leads to an explosion. Now, depending on the mass of the star, the object that is the resultant, that results from this incredible force of the star's collapse upon itself, upon its core, the object could either be a neutron star or a black hole, depending on whether the internal components of the matter are able to resist, give an outward push successfully to the imploding matter, or whether they simply can't resist that. So you're going to either have a black hole or a neutron star. So if the star is more massive, you'll have a black hole. Otherwise, you will have a neutron star. A neutron star is essentially a gigantic city-sized atomic nucleus with protons and neutrons inside it. Lots of protons and neutrons squashed together. So it has the size of a city, let's say, roughly 10 kilometers or something diameter, but it has the mass of an entire star. Tremendous gravity. So it's a gigantic atomic nucleus, and inside it you have protons and neutrons. Now, protons and neutrons, they are made up of something called quarks. Quarks are fundamental subatomic particles, fundamental particles. And you have six kinds of quarks: up, down, strange, charm, top, bottom. Six different kinds of quarks. And the matter that we are familiar with, it is it is only composed of two different kinds of quarks, up and down quarks. So protons are UUD, two up quarks and one down quark. And neutrons are UDD, one up quark and two down quarks, triplets. And quarks have something called confinement. They're confined together, and no matter what you do, they will always stick together. You will never find free quarks anywhere. And this color confinement. It's called color confinement. And if you try to break two quarks or three quarks apart, you have to give tremendous amounts of energy, and that energy will be used to generate more quarks, which again stick together. So that's what you have. Now, it is possible that inside neutron stars, where the density and pressure are incredible, you may have deconfinement, which means that the protons and neutrons dissolve into their individual component quarks, which swim around freely, because the environment inside the neutron star is so incredibly dense and the pressure is so incredibly high. So you may have deconfinement inside a neutron star. Okay, I'm coming to quark matter. I'm coming to that. I'm coming to strange matter. So I said there are six kinds of quarks: up, down, top, bottom, strange, charm. Now, it is possible, and the two stable forms of quarks, kinds of quarks, are up and down. The other ones, they decay. Now, it's possible that inside a neutron star, where you have quark matter, deconfined quark matter, because of the pressure and various conditions, you may have some quarks getting converted into strange quarks. And strange quarks have very strange properties, and they could, combine with other quarks, and they could form extremely stable matter, maybe the most stable matter that exists anywhere in the universe. And they could possibly convert other quarks into more strange quarks. But generally, so that is strange matter, which is a combination of the standard quarks with a strange quark. Um, so that is what strange matter is, but that obviously is matter that would be at the heart, that would be inside, confined inside a neutron star. From outside, the neutron star looks just like a standard neutron star. We don't know what's inside. Inside there could be strange matter, strange quark matter. Now, when could this strange matter be be exposed to the universe? So when you have neutron star collisions, which are incredibly energetic phenomena, that's when the insides of neutron stars are spewed out into the universe. When you have the collision of two neutron stars, they spiral around each other. There's an in spiral, and they eventually collide. So that is one way where strange quark matter could be ejected into the universe. The other phenomenon is the collision between a neutron star and a black hole, which also could result in some part of the neutron star being ejected out into space, and the rest would be absorbed by the black hole. So in that case, you would have strange matter traveling across the universe in strange matter droplets called strangelets. So that is strange matter. Okay, that's strange matter. It has strange quarks, and it is theorized to be extremely stable, the most stable matter that you can have in the universe. And if strange matter comes into contact with regular matter, ordinary matter, it could turn your ordinary matter into strange matter. So if a strangelet, a droplet of strange matter would hit the earth, it could turn the earth into strange matter, and all life would disappear. We would all become strange. It could, if a droplet of strange matter were to hit the sun, it could turn the sun into a strange star. The entire matter of the sun could become strange. Okay, and what happens to a black hole if strange matter comes into contact with a black hole? Well, I'll tell you something on black holes. A black hole, the properties of a black hole are described by only three quantities: mass, charge, angular momentum. Mass, M; charge, Q; angular momentum, L. Those are the only three properties that a black hole that can describe a black hole, nothing else. So it doesn't matter what goes inside a black hole, strange quarks or standard quarks or whatever. It doesn't matter. It makes no difference. So a black hole will not become a strange black hole. It will just become a larger black hole. It will swallow the strange matter. It will become a larger black hole. That's it. It will not turn into strange matter. It will remain a black hole. The only change could be to its mass, charge, or angular momentum, depending on how the infalling strange matter entered the black hole. That's it. Nothing else. All right. Asha Kashyap says, why are all the planets in our solar system round in shape while comets and meteorites are kind of uneven? So I'm sure I've answered this question before, but let's take it again. There is a phenomenon called hydrostatic equilibrium. So what happens is that when you have a large enough object with large enough mass, then the gravitational force of the object that it exerts upon its constituent parts, it becomes stronger. The gravity of the object becomes stronger than the structural strength of the materials that make it up, that are part of it. So that's how the object becomes spherical, because the most the most perfect shape that you can have of any object is a sphere. So the gravitational force of the object, it defeats the structural strength of its constituents, which is the rocks and whatever else that you have in the object, and that's how it becomes kind of spherical. So a sphere, essentially, like I said before in a different answer, it has the smallest surface area for a given volume and the lowest energy state. And nature wants the lowest energy state. You can think of it that way. And that's how planets become spherical once they acquire a certain mass. So it's about hydrostatic equilibrium. But when it comes to objects like asteroids and meteorites and meteors and comets, etc., these are too small for the gravity of that object to defeat the internal strength of the material, the rock, and whatever else it is. And it's also the fact is that these objects are left over from the initial stages, the initial uh, era, which was the birth of the solar system, and maybe these objects, they never were able to come together and coalesce together, which would form planets. So that's why these smaller objects are not spherical in shape, while the larger planets themselves are spherical in shape. Yajnavalka says, do you have doubts about whether you are a Boltzmann brain? A Boltzmann brain is a philosophical concept. It's a concept that's not, well, it's related to statistical mechanics, etc. So the concept of a Boltzmann brain essentially is, it says that a Boltzmann brain is a disembodied brain. It's a hypothetical self-aware entity that spontaneously arises because of random fluctuations in the universe, or in a vast universe over an immensely long time scale. So in an enormously vast universe with immensely long time scales, Random fluctuations could spontaneously create an incredibly complex structure, including something as complicated, as intricate as a brain with self awareness and memories of a life that it has lived, which it actually has not. It just spontaneously arose because of random fluctuations. So, statistical mechanics tells us that if you have enough time, given enough time, and given every possible state of matter, no matter how improbable, everything, any possible state of matter could emerge in the universe, given enough time. So the probability of something like this happening is extremely low, but not zero. It is a non-zero probability. So over an almost infinite time scale, a brain, you know, a fully functional disembodied brain with false memories of having had an entire life could actually appear spontaneously. So that is the concept of a Boltzmann brain. It's a philosophical concept, and that kind of yeah, it raises various kinds of questions about existence and so on. But I've never had doubts about whether I'm a Boltzmann brain. I've never thought that deeply. But yes, it's an intriguing question and possibility. Okay, with that, I'm at the end of the questions that I've taken from the comments. Now, if you have some questions in the live chat, go ahead and I will take a few. And let's try, okay, let's try and take questions that I have not taken before, but that would be difficult to find, I'm sure. Shri Vatsa says, if white dwarfs turn into black dwarfs, what will neutron stars turn into? Hmm. So white dwarfs will eventually turn into black dwarfs. A white dwarf is essentially what's left over from the death of a small star, like the sun. So the sun, our sun, will not go supernova. It's too small to go supernova. It will simply eject. It will eventually, in about 5 billion years from today, become a red giant, red giant, and then it will eject its external layers into what's called a planetary nebula or something. And at the core will be left what is called a white dwarf, which is a gigantic carbon crystal, extremely hot incandescent carbon crystal, a gigantic diamond essentially. And over billions and billions of years, it will lose its heat and eventually turn into a black dwarf. That will happen over, I don't know, billions or maybe trillions of years. So that's the eventual state, that the fate of the sun, a black dwarf. First a white dwarf, then after an immensely long period of time, a black dwarf. What will neutron stars turn into? That's a fascinating question. So neutron stars, what could they turn into? I think they will remain atomic nuclei. They may lose their heat, but they will remain gigantic macroscopic atomic nuclei. As long as there is no collision with other neutron stars or other objects or black holes, they will simply continue to exist. They don't decay, they don't evaporate, they stay what they are. They may lose their heat over incredibly long time scales, but I don't see neutron stars turning into something else. They will remain atomic nuclei. Interesting question. Interesting. Um, Sushil Matre says, what's quantum entanglement? Quantum entanglement is a very strange quantum property. Uh, Essentially, what happens is that, look, every quantum object, whether it's an electron or a proton or whatever, it is described by a wave function. A wave function is a mathematical object that describes the probability of it existing at various points in time at various locations in the universe. That's the wave function of a particle. Okay. Now there are certain. Sometimes what happens is that you have entangled particles, which means that these two particles are described by a single wave function. So they are entangled. They cannot be described by two separate wave functions. They can only be described by a single wave function. And that means that they are entangled. What does that mean? It means that if you observe one particle, you will immediately know the state of the other particle, the corresponding particle, instantaneously, no matter where it is. Even if it is 100 light years away, you will instantaneously know it, what the state of the other particle is, of the other entangled particle. So it's like having a pair of gloves, a left-handed glove and right-handed glove. You put them in two separate boxes. You shift one off to Moscow, you shift the other off to Washington. Your friend in Washington opens it, He or she finds a right-handed glove, he or she will immediately know that your friend in Moscow has received a left-handed glove. That sort of thing. That's a very rough analogy that describes the entanglement phenomenon, but it's not exactly like that. And um, there is no transmission of information in entanglement, contrary to what some science fiction TV shows show you, but that's essentially what quantum entanglement is. um, VRV says, is time a mind construct as we experience past, future only in now? Look, time is one of the biggest mysteries in science, in physics. Okay, and we don't know what time is. Is time something that emerges? Do we have atoms and molecules of time? Is it an emergent property of the universe? Is it something that's external to the universe? I mean, if you look at quantum mechanics, time is an external parameter. Okay, time is an external classical parameter in quantum mechanics. It's not something that emerges out of quantum theory. So we don't know what time is, and we perceive it only vaguely, very hazily. And yeah, our actual perception of the world is what's happening right now. But it's because of consciousness that we have memories, and that's how we can travel into our memories and even speculate about future time scales. But what's happening is right now. So we don't know what time is. Is it a construct of the mind? Does it emerge? Is it a consequence of quantum entanglement and decoherence? We don't know. We don't have answers to this question. It's a fundamental, profound mystery in physics, in science, and we don't have the answer. But that's why it's so fascinating. That's why physics is so fascinating, because we don't have answers to such profound questions. um Dheeraj Kamath says, there are reports that Dyson spheres or swarms may have been discovered around stars in outer space. What are your thoughts? What's the likelihood that these alien civilizations know us? Okay, let's understand what's been discovered. There's been a recent paper, reasonably recently, in the monthly notices of the Royal Astronomical Society, MNRAS, which is a good journal. So a paper has been published there, and what they were looking for. So what's a Dyson sphere? Sphere, first of all, a Dyson sphere is this hypothetical, gigantic engineering construction in which you have these panels that envelop a star completely, so that you can absorb, you can trap all of its energy and use it for whatever you want to use it. So you would need to be a hyper intelligent civilization with superhuman engineering capabilities to be able to construct that structure that can completely envelop a star. Okay, and then you can use all the energy of the star. Then you can use all the energy of the star. It's at your disposal. That's what a Dyson sphere is. It is a feat of super engineering, which we simply aren't capable of right now. Now, what if there are civilizations out there, alien civilizations that have constructed Dyson spheres? Then what would that look like from here? That's the question that scientists would ask themselves, astronomers, astrophysicists would ask themselves. And the answer is, if you have a star that's enveloped completely in this structure, Dyson structure, Dyson sphere, then that structure will get hot. It will emit infrared light, this glow of heat glow, which is infrared light. So what about we look for that? We know what the characteristics of that glow are like. And we don't need to build new instruments and telescopes to look for it. We have tremendous amounts of data that we already have at our disposal from all the experiments we've done in the past. We have data for billions of stars. So why not just go through all the data and search for those signatures? So that's what this study did, and I think they came up with a number of a dozen or 2 dozen or so candidates for Dyson spheres. So it doesn't tell you that these are genuine Dyson spheres, but they are showing the characteristics that you would expect a Dyson sphere enclosed star to exhibit. But there are other, possibilities, other possible explanations that could for the same phenomenon. Just a gas cloud that's very hot for whatever reason. There are so many other ways by which you could explain what you're observing here. So it is not definitive evidence of Dyson spheres, but it's an interesting study. who knows, some of those may actually be Dyson spheres. So my thoughts are that we have to be skeptical, we have to be careful in science. You don't jump to conclusions, you have to look at all possible explanations, and first take those explanations seriously that are more plausible, like a gas cloud that is hot or whatever else. The least likely possibility is an alien civilization with a Dyson sphere. So that's how I see it. Uh, but in case some of these are actual alien civilizations that have constructed Dyson spheres, that would indicate that they are incredibly way more advanced than what we are today. And I don't know if they know us. I hope they don't. I hope they don't, sir. Okay, let's take maybe one or two questions. One or two more questions. What else? What else? What else do we have? Om Bekerekar says, in the movie Interstellar, Cooper, the protagonist, sends coordinates to the past through the tesseract. Does this violate the law of causality, or is it a predefined loop? What happens when he goes there for the first time? What happens so the tesseract is something he encounters inside a black hole, right? He jumps into a black hole. And inside the black hole, he crosses the event horizon. There is a tesseract apparently in there, and he sends coordinates back to the past through the tesseract. Does this violate the law of causality? It does violate the law of causality. It could violate the law of causality. So until you can determine the problem exactly, you don't even know whether it's a causal loop or whether it is violating the law of causality. But when you do things like going back in time and all, you do end up violating causality, and that raises the question as to whether causality is one of the laws of the universe. As far as we know, everything has a cause, every effect has a cause. So is the universe causal in nature, or even quantum mechanics does seem to sometimes violate causality? So yeah, we're not sure if the universe is local, if it is causal and all that. But when you send information back in time, you do time travel, all that, you do end up violating causality. So that's what I would say. Okay, let's take one more question before we end. Karan Nalawat says, your all-time favorite physicists and mathematicians. Mathematicians, Euler, Ramanujan, Harvey, Perelman, Grigory Perelman, so many more. Physicists, obviously, you would have to say Einstein, Niels Bohr. Without Niels Bohr, he would not have quantum mechanics. He was one of the giants on whose shoulders we stand today. So definitely Niels Bohr, Heisenberg, Schrödinger, Oppenheimer. Why not? Sudarshan, George Sudarshan, great guy who should have won 3 Nobel Prizes. 3 Nobel Prizes he should have won. Then you have Chandrasekhar, obviously. Hawking, sure. Lev Landau, and so on. Yeah, a few, just to name a few. Obviously Feynman, obviously Pauli, Wolfgang Pauli. I'm sure if I think a little bit more, I can think of many more. Anyhow, yeah, let's end this session with that question. We've crossed 2 hours once again. So yeah, that's the end of today's session. I apologize to those of you whose questions I'm not able to answer. I can see so many more, but I'm going to end it over here. But we're going to keep doing this, so you can keep asking questions and we'll take as many as possible. All right. So thank you so much. And I will see you in the next live stream, which will be tomorrow. And it's a totally different topic. It's history, geopolitics, and current affairs. So hope to see you there. If not, in the next week's science live stream. So take care, and I'll see you soon. And keep raising your standards, keep asking questions. See you soon. Bye.